Okay, welcome back to lecture 2 of part 3. In this lecture, we're going to talk about characterization and monitoring. As a quick refresher from the last lecture, we are following the radiology workflow, and we are talking about image-based tasks, which we can divide into 3 categories: detection, which we covered in the last lecture, and then characterization and monitoring that we're now going to talk about in this lecture. Characterization represents the radiological assessment of the quality and quantity of image features as it relates to diagnosis or staging of a given disease. So it's probably the more important function of the radiologist. And these tasks are accomplished by quantifying and qualifying the radiologic characteristics of specific abnormalities or areas or regions of interest. And from a quantitative perspective, what will be taken into account is the size, the extent, the internal texture of these areas. Now you must be thinking, radiologists are successful at characterization, and so why would we need to consider artificial intelligence machine learning in order to assist the radiologists or even quite possibly to replace them? Well, one of the first reasons that come to mind is that the human brain is only capable of handling a certain number of tasks at one time. Now, yes, it may vary between radiologists, but the range in which humans operate is much, much less than computers. And theoretically, for computers, as the technology improves over time, the number of tasks it can actually handle at a given time, at a given moment, will increase infinitely. Additionally, there is in the foreseeable future, the possibility that computers will actually exceed the capabilities of radiologists in terms of discrimination or in terms of identifying abnormalities and making the difference between an abnormality that is malignant, let's say, and one that looks different than normal tissue but is not malignant. And I think that's probably one of the biggest challenges currently, is that something will look abnormal but we're not quite sure, and it needs to, so then it gets pushed back, and then it will need to be tested again in the future in order to confirm. And quite possibly, as we move forward with artificial intelligent solutions, that computers may be able to more readily discern the difference between abnormal and normal tissue. So this, of course, would be a huge advantage. So not only being able to juggle multiple tasks at the same time. So meaning the ability to retain qualitative features that need to be assessed for every image. Inevitably, as the technology increases and the resolution of the images increase, and the modalities may actually change as well, improve over time, which will give more image features to take into account, it is going to become more and more challenging for radiologists to keep all of that in mind when they're assessing an image. So there's that limitation, and then coupled with what they're limited to in terms of what they can see with the human eye, quite possibly artificial intelligence will be able to not only handle all of those features with ease, but also be able to consider features that are just not available to the human. Finally, of course, as I mentioned earlier, we have the problem of radiologists the variation in the radiologist. So meaning you have a well-trained, very expert radiologist, and then you'll have, unfortunately, a radiologist that's not as well-trained and not as good as what they do. And so that causes a problem in terms of delivery of healthcare. Whereas computers, the standard is always the same essentially because it is not dependent on human variation. In the last slide, we suggested that through automation, artificial intelligence would be able to consider an ever-growing large number of qualitative features when performing this task of characterization, and at the same time be able to do it in a reproducible manner and never suffer from fatigue. So this is a great advantage to AI, where humans, though they do a wonderful job, it is less reproducible, and they will fatigue. So meaning if you give them too many tasks to do over day after day after day, they will fatigue and their performance will suffer. Now, AI can also automatically identify these features, of course, as we've said, and many others. And the ones that I was referring to as possibly something that the human eye can't necessarily pick up are what we would call an imaging biomarker. And let's talk a little bit about that. So an imaging biomarker is a biological characteristic that is detectable on an image, as simple as that. Now, imaging biomarkers can be anatomical or functional, and they can be qualitative or quantitative. We can also have several imaging biomarkers that will contribute to a given response criteria. So here's a first rule of thumb, is the imaging biomarker has to be linked to some decision process. So meaning that the identification of this characteristic is going to contribute to making, for instance, a diagnosis or making a decision of what to do next. So that's an imaging biomarker. Now, let's start talking about a very, very simple stage, I guess, to developing a biomarker, and that is segmentation. And segmentation in radiology there's nothing new to it. It started in the 80s and has continued ever since. Now, the very basic early segmentation algorithms used to, simply, cluster imaging intensities, I try and isolate different areas, or utilize what's called region growing, which is where you would have a seed which could be user defined. So meaning, you click on it, and then from that seed, the area of interest would grow around it until the user was satisfied, and it would be based on certain criteria in terms of texture, homogeneity, intensity, and that would be the early forms of segmentation. So where are we at with segmentation? Well, the first barrier is a common one, and that is if you develop a tool like segmentation for research and use it in research, that's one thing. If you want to use that tool in the clinical setting, it's another. And the difference is regulatory compliance or expectations of how consistent, how reliable, and how meaningful that tool is. And so far, segmentation has been very successful in research. However, when you want to cross over into clinical, there is a requirement for higher specificity and precision, of course. And for example, if you use segmentation in radiation oncology, you need a very accurate and precise delineation of both tumor and non-tumor tissues, because you need that margin in order to do correct radiation treatment planning. And so far, attempts at automating segmentation have made their way into clinic, but it's with varying degrees of success and varying degrees of utility, if you wish. So where are we at for introducing artificial intelligence and machine learning into segmentation software? So here's an example of a group working with brain MRIs and segmenting gliomas, which is, the most common malignant brain tumor. And their intent was to not only segment, but to also grade these tumors. And in order to achieve this, they performed what's on the slide, which is their pipeline essentially for segmentation and grading. And they used the convolutional neural network, which you guys are all now experts in, based on our last lecture. You can see in their pipeline here that they have their input images, which they then process and detect within their image a region of interest and segment it, and then they will follow it up with the selected images of interest and grade them as their output. So actually there are two outputs. There's the segmentation output, and then there's the grading output. The CNN architecture that they used was called UNET, and UNET is probably the most popular, common, successful architecture used today for segmentation. You can see on the bottom right of the figure what the layers are, and you can appreciate in terms of the shape of the architecture that it looks like a U, and that's why it's called UNET. Coming back to our example of using brain MRIs to segment the glioma tumors, the authors of this project were able to demonstrate that the use of this CNN architecture, UNET, was very successful in not only segmenting the tumors, but also grading them, which of course is very beneficial to treatment planning. Other successful applications of this CNN architecture would be the creation of probabilistic atlases for locating diffuse low-grade gliomas in brain MRIs, as well as volume estimation in prostate MRIs, or assessment of head and neck CTs for radiotherapy treatment planning. And further, if on expansion of this deep learning architecture, so the UNET we've already talked about for segmentation, could also lead to a full output segmentation probability map across an entire image. So while we've seen much success in the segmentation of non-diseased organs and tissues, when we want to identify the extent of a diseased tissue, the challenge for the segmentation algorithm increases by a lot. And the reason for that is, or some of the reasons for that is, there are no landmarks possible because you don't know where the diseased tissue is going to occur, as well as the difference between a diseased tissue and a regular tissue may actually be very subtle, and therefore it is much more challenging in order to train that algorithm. So currently, much of the segmentation software that's out there relies on high-level matrix in order to make decisions or to provide identification. And this is where there is the hope to find image biomarkers that can be used along with other clinical endpoints in order to predict malignancy. So another example of biomarker is Pyrads for prostate cancer. So Pyrads is a standardized reporting system for prostate imaging, very similar to the BIRADS for breast imaging. And the Pyrads promote standardization for the reporting of multi-parametric MRI features. And a recent study that used these Pyrads found a sensitivity of 74% and specificity of 88% for detecting prostate cancer using Pyrads, which is actually quite fantastic because it would allow to minimize primary biopsies, which are very invasive. So here's an example of where image features on MRI are acting as biomarkers for the later use in either staging or diagnosis or detection. So where are we going with this software that provides characterization of image features? Well, inevitably, software like segmentation software that is leveraging artificial intelligence and machine learning will continue to improve, will continue to become more accurate, more reliable, and therefore more useful. Additionally, the ability to create probabilistic atlases will become a more and more attractive option when the regions of interest are ill-defined or difficult to assess or distinguish from similar tissues in terms of their pixel intensities. Let's move on from characterization to the last stage, which is monitoring. Now, this is a relatively new area of focus for artificial intelligence and machine learning, and the reason for it is because it involves a new dimension, the dimension of time. All of the solutions to date for detection and characterization have involved a static solution. So meaning that it's determining an answer is providing you with an impression from a single image in time. So like a static single image. Monitoring is essential for diagnosis as well, and especially for the evaluation of the response to treatment. But what it does is it's looking for progression of disease or improvement or regression of disease. In order to do that, you need to compare an image that you see today with one that you measured, let's say in the previous visit, which was either a month ago, 3 months ago, 6 months ago, even a year ago. And by monitoring these images over time, you are looking for instance, a trajectory. So what is the disease trajectory? Is it improving? Is it getting worse? Is it cyclical? And this workflow will require pretty much image registration and pre-processing for most, if not all, modalities, and that is tricky. The other challenge is we need to decide on, what metrics to use to determine, progression or regression. That's fairly straightforward. So once we've, registered the images, so you've got the previous, visit image and you have the current visit image, and you register them so that you can compare them, then you need to decide on the metrics in order to decide, to measure, change, right? So that's fairly straightforward. However, the piece that's going to be challenging for artificial intelligence and machine learning is that the neural network that we've been talking about all this time, the deep learning and all this, the CNNs and all this wonderful stuff, one of the assumptions that is made is that the inputs are independent, or if you wish, the outputs are independent. So meaning that once it's done, gone through one, it's assessed one image, the next image is independent. And so that's a problem because you want to look at two images and say, okay, where's the change? And so there are some solutions, and probably the most focused on right now is recurrent neural networks, or RNNs. And these ones are very, very well known in the world of natural language processing. So trying to guess the next word is done by recurrent neural networks. So when you're typing on your phone and you're writing to something, blah, 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 and then it guesses what the next word is, and it's just it's slightly grayed out, right? But it's available for you, and you can just tab forward or just accept it. That is done by recurrent neural networks. And so now applying this to imaging is tricky, challenging, and very computer intensive. So recurrent neural networks, or RNNs, can evaluate an input sequence in such a way that responses to earlier parts of the sequence are taken into account at the same time as the processing of your current input. So what this means is that essentially the evaluation results of previous sequence elements are taken into account at each step of a sequence. And this is why the RNNs are described to possess memory. Now, there are limits to this, of course, and you think, oh, wow, you can probably go back and have as many sequences as possible. The problem is that's not really the case because just computationally that's not possible. And so you pretty much are working with a few, sequence elements that you can quote unquote retain as you're processing. Data such as time series have a sequential order that needs to be followed in order to understand. Now, the traditional feed-forward networks that we've been discussing cannot comprehend this, as each input is assumed to be independent of each other, whereas in a time series setting, each input is dependent on the previous input. And if you remember from statistics, the closer they are in time, the more highly correlated they are, which is called autocorrelation. So in the illustration on this slide, we can see that the neural network with its hidden state S takes an X input and outputs a value O. The loop that you can see here on the RNN cell shows that the information is being passed from one step to the next. And if you look to the right, you can see that state xt, which has an output ot, has to the left, state x t minus 1, and to the right, state st plus 1. And it is in this way that we will be able to leverage RNNs to produce images or predicted images from a time series. So what would be the predicted next image from this time series? So this brings us to the end of lecture 2. A lot of technical information in these 2 lectures, or in part 3. And I hope you take the time to try and understand a lot of it, most of it, all of it, as much as possible, because it will be very helpful for you when you engage in discussions about artificial intelligence as applied to medicine in order to contribute to the conversation, instead of just being a bystander saying, I've heard those terms, but I'm not quite sure what they do, and so I can't really contribute. That was the purpose of part 3. Now, next in part 4, we're going to learn how to critically review AI/ML publications, as well as go over the ethics of the use of data in AI/ML projects, and policy and data governance. See you there.